Hi guys, Dr. B here. This is topic 2.2 for AP Chemistry, intramolecular force and potential energy. Intra, that prefix means it's within the molecule. Later on, we'll talk about intermolecular forces, and that's between different molecules. This is the force, or talking about forces within a molecule. The objective is to be able to represent the relationship between potential energy and distance between atoms based on factors that influence the interaction strength. We're going to be graphing potential energy and the distance between atoms as a way to describe interactions between atoms. We're going to focus on bond length, potential energy, bond energy, etc. And we'll also talk about Coulomb's law as well. Covalent bonds, like we said, are bonds between two nonmetals when they share valence electrons. They can be polar or nonpolar, meaning, the shared or equally and unequally stuff. Covalent bonds can be single, double, triple bonds, or an average of those if there are resonance structures. We'll talk about that like 2.5 or something, 2.6. Covalent bonds occur at the lowest energy state. This happens when the attraction between the nuclei is the greatest for the shared electrons, but the repulsions between electrons and the nuclei is the least. If the atoms are too close together, they will repel each other. If they're too far apart, there will not be enough attraction to hold them, and is shown in the graphs below. So we see that on the y-axis we have potential energy, and on the x-axis it's going to be internuclear distance, meaning the distance between nuclei. As you see in this graph here, this one here, you can read it from right to left, here then there, okay? So as the distance increases, as you can see by the two H's here, for example, the amount of energy, potential energy, is not that great. It's very minimal. As that nuclei get closer and closer together, right around here, you can see that it's at a specific bond length that there is the greatest potential energy, so to speak. Meaning that at this point, it's the most stable for the two nuclei that are involved. Notice when it gets closer and closer and closer, the potential energy becomes positive, meaning that there's enough repulsion now that they will just go apart. Bond energy is the energy when breaking a bond, or the energy released when a bond is formed. The magnitude is the same, but the sign is different. Larger atomic radii increase the bond length. Longer bond length decreases the bond energy. Increasing the bond order increases the bond energy, as there are more electrons involved and therefore greater Coulombic attraction, and the bond length has decreased. So here's some average bond enthalpies. You don't have to memorize these. They would give these to you on the test, whether it's in the FRQ or the MCQ part. So there's some that you should probably recognize or like be able to know. So like you have the single hydrogen bonds, double carbon, double carbon, single carbon, a triple nitrogen bond, double oxygen, etc. Bond enthalpy, just so we know, is the amount of energy that's stored in a bond between atoms in a molecule. It's also known as bond dissociation enthalpy. Here are the average bond lengths in a single hydrogen bond, double carbon, triple nitrogen, double oxygen, etc. So the general trend, comparing like nitrogen single, double, triple, the more that you increase the bond order, meaning there are more bonds involved, more electrons involved, the distance gets smaller. In ionic compounds, lattice energy is the energy to separate ions in ionic compounds. It is defined as the change in energy that takes place when gaseous ions are combined to form an ionic solid. Combining ions will release energy. Lattice energy can be represented using some kind of modification of Coulomb's law, where the energy is proportional to the charges and inversely proportional to the distance between the nuclei. Larger charges, more attraction, more energy required to separate bonds. Smaller radii, more attraction, more energy required to separate bonds. The bond energy for a carbon double bond is 614 kilojoules per mole with a bond length of 1.34 angstroms. It is shown on the graph below. Sketch a carbon single bond to another carbon and a carbon triple bonded to another carbon. Include a key. So usually when you have to draw a graph, you have to indicate that there's a key, or you have to use a key to indicate which one you're talking about, and that's the general expectation. So if you're going to be drawing a graph, it may not even ask for a key, but it's implied that you use one. So looking at this, you'll notice that there's no like units or a scale on the side. These are just general. It's a kind of a quantification, I guess, or whatever. So basically, this is whatever you can use the same drawings for multiple graphs, for example, but the labeling is the important part of what your graph is showing. So if we know that this is the carbon double bond, so we say that, okay, so we have our carbon double bond is the solid line. We have to do the carbon single bond and a carbon triple bond. So you have to indicate with a key what it is. So this could be my single bond, triple bond will be my, like, just a bunch of dots. So remember that if this is the internuclear distance and this is the potential energy. Between two carbons, if it's a single bond, let's actually hold on. Single bond between the two of them, the distance between the nuclei is going to be greater than a double bond. So that means we know that our dip, we're just going to follow the same pattern, is going to be somewhere over here. Less energy will be there as well because there's less electrons that are being shared. So it's going to be in the same general area as that, but then it's going to drop a little sooner. There we go. And then go up. And that's going to be my single bond. In the triple bond, more electrons are involved, greater energy for that, and also smaller distance. So same here. We're going to drop it about here and then go up like that. So that's going to be my triple bond. More energy involved and shorter distance between nuclei. One way to identify an unknown substance is the measure of the bond energy. Hx, Hy, and Hz are analyzed and the following graph was created. It is known that these are Hi, HCl, and HBr. Use the graph to match the unknowns with the knowns. So we have to think what, based on our knowledge already, we have to interpret the graph. So we know we have an Hx, Hy, and Hz. We have to match with Hi, HCl, HBr. So the best way to do that, notice how this can look similar to the previous one that we just did, but now by just changing what is involved by labeling, we're changing what the graph is. And it's the same shape, same scale probably, but in the end, the labeling and identifying what those things are, that's where you're able to get your general understanding of this type of graph. So looking at this, notice they're all halogens involved, all halides. So we can't really tell the energy from these, but we can know the we can use an internuclear distance to help us out. So for the internuclear distance, we notice that it is technically increasing from left to right. So between H, because if the H's are all the same, like this, the one that's going to be different is going to be the I, Cl, and Br. So the greater the nuclear distance, the further to the right it will be. Knowing the atomic radii for each of these elements is key. So that means that Hz has to be Hi because it has the greatest distance, the greatest atomic radius. Therefore, Hx will have to be the smallest one, which is going to be HCl. And that leaves us with Hy to be HBr. All right, that's it for now. If you have any questions, let me know. Thanks.